Any object that is oscillating undergoes a transfer of energy. So for a spring that is oscillating, a spring oscillator, there are points where the object is moving the most, and there are points where the object stops moving. And so if we consider this position time graph for an object that is attached to a spring and oscillating back and forth, the maximum displacement is here, and this is where the velocity would be 0 because the slope of that line is 0. So the maximum displacement, we have this 0 velocity. So that means that all of the energy in the system is stored energy. So we can consider creating a energy bar chart in which the mass and the spring will be part of my system. And initially, if we are considering when the object is at the maximum displacement, so when our mass is far to the right here at a positive position, we'll have all the energy stored as elastic energy, so energy stored elastic. And then if we consider when the particle or object moves back through this equilibrium position, so this point right here, this is 0 on my axis, which would correspond to 0 here. And then it will continue to move through to this negative position here. But at the moment that it passes through the equilibrium position, this equilibrium position here, all of the elastic energy is now kinetic energy, or energy stored in the motion. So the energy equation would look like 1/2 K A squared is equal to 1/2 mv squared. Now I used A to represent the amplitude because that's the maximum position. So we could then determine the speed of the object as it passes through the equilibrium as being the square root of K A squared over m. Let's look at another case where we have stretched the spring out to a maximum position, A, and then we're going to release it. So let's look at what the speed of our object would be as it is moving. We've released it, and it's moving and located at the half amplitude location. So this will be our equilibrium position where the spring is not stretched or compressed anymore. So let's draw a energy bar chart. Let's treat the mass and the spring as our system. And so initially we have all energy stored in the stretch of the spring, and I'll call that my elastic energy. Now, at this position here, it is moving and the spring is still stretched. So some of the energy that was initially stored has remained stored because it's still stretched. So I'm just going to write this like that, and I'm just arbitrarily choosing 2 bars at this point. And then because it is moving, I'll give it the rest of the bars are the energy stored in the motion. The equation for the energy transformation will look like this. So now we can solve for the velocity. So I've multiplied by 2 on both sides and squared my a over 2. Subtract k a squared over 4 from both sides. So we can solve for velocity, which will be the square root of 3/4 k a squared over m. Now, how does that compare to the maximum velocity? So what was the velocity in terms? It's the square root of Ka squared over m. So then we can compare that to our velocity we found at a over 2. So then the equation on the right would be the square root of 3/4 times the square root of Ka squared over m. And that means that this velocity at the halfway point is equal to V max, because this is our maximum velocity, which would be that term there, times the square root of 3/4. It's important to note that the velocity at the halfway point is not equal to half of the maximum, but actually it's greater than half of the maximum. So where's the object when the velocity is half of the maximum? Let's create a LOL chart. Our system again is a mass and a spring, and the energy stored initially would be all elastic energy. And then as it moves through this position here, there's some energy that is still elastic, and some of the energy is kinetic. Again, I've just drawn my blocks to represent the relative magnitudes and not the exact magnitudes. Now, earlier we defined this maximum energy as being 1/2 Ka squared, and that would be equal to 1/2 v squared, the maximum velocity there. So I could write my energy transformation equation in terms of that maximum velocity. So m v max squared is equal to 1/2 K x squared. This is where it has half of the maximum velocity. So it's still moving. We'll have 1/2 m, and this will be v max divided by 2. And don't forget to square the whole thing. So multiply by 2 on both sides, and then square out the v max over 2. We can solve for x. Would then give us a square root of 3m v max squared over 4k. From earlier, we have that the v max is the square root of Ka squared over m. I can pull the v max squared out of the square root. Then we'll substitute in our v max expression from earlier. Let's simplify. Simplifying, we'll have 3/4 a squared under our square root, because the k and k canceled, and the m canceled. So we get that the position would be the square root of 3/4 times the amplitude. This is where our object is when the velocity is half of the maximum. So let's look at another case. Where is the object when the kinetic energy and the elastic energy are equal? Again, we're going to release the mass from the amplitude. We'll make an energy bar chart. The mass and the spring are in the system, and initially all the energy is stored as elastic energy. So I have 1, 2, 3, 4, 5, 6 bars of energy. And in this case, the energy later will be equal kinetic and elastic. Then I'll make this my elastic energy later, and this is my kinetic energy later. So I've got 3 bars of each. Now this time I knew how many to put in each place based on the setup of the question. Writing the equation out, I get 1/2 ka squared is equal to 1/2 kx squared plus 1/2 mv squared. And at this point, the kinetic energy is equal to the elastic energy. So then I can write my equation as 1/2 k amplitude squared is equal to 2 times 1/2 kx squared. Simplifying, I get a squared over 2 is equal to x squared. So x would be the square root of a squared over 2, or a times the square root of 1/2. Again, notice that the place where the energies are equal is not at half the amplitude.